Kuzambo, welcome to Bhutan e-learning project. This is a physics lesson for Key Stage 4, classes 9 and 10. My name is Funso Chodin. For today's lesson, I brought along my son and daughter. So guys, can you introduce yourself?
Uzampola, my name is Duxel.
Example, my name is Tichin.
We need energy to perform all kinds of work, right from picking up a pencil from the floor to lifting heavy objects. And work cannot be done without energy. Human beings derive energy from the food we eat. Likewise, machines derive their energy from the fossil fuel or from the electrical energy. And in many situations, the time taken to perform a work is just as simple as the amount of work being done. Hence, the concept of power incorporates both work and time. So, my dear children, have you guessed what we are going to learn today? Yes, today we're going to learn three very important concepts in physics: work, power, and energy. It is usual in physics to speak of the work done by a force, whereas in everyday life, work is seen as being done by people. You need to remember that a force is not a thing or a person, it is an action. And all the changes that take place around us are the result of force. So we all know that forces can make something move, can change the shape and size of an object, or change the direction of a moving body. Now, if you apply a small force, then that may not be able to bring any change in a huge body, even though you're applying force. So in such case, work is not done. So then when is work done? So now I'm going to take help of my two kids and then demonstrate different cases of work done. Alright, so let's see the first demonstration. Are you ready, Dichen?
Yes.
Okay, so Dichen, I want you to push that trolley slowly and come till this point. Alright, so in this demonstration, you got to see two things. One is the force applied by Dichen, and due to that, the trolley is moving, which is the displacement. And here you notice that the direction of the force and the direction of the displacement is same. So in such case, work is said to be done. So we have seen that for work to be done, there should be force and displacement. Now we're going to see what is going to happen if either force or displacement is not there. Okay, so for that, I want you to lift this trolley and not move.
Okay.
And you're going to stay like this for a while. And are you tired?
Yes.
Yes? Do you think you have done work when you lifted the trolley like that?
Yes.
Okay, so see, this is the misconception. We usually feel that, you lift heavy object, you have done a lot of work, but scientifically, this kind of work is zero, which means you have not done the work. Now, why? Now, see this example? When you lifted the trolley up, the direction of the force was upward. So there is force, okay? But he did not move, which means that there is no displacement. And if there is no displacement, even though you have applied the force, this kind of work done in physics is zero. You have not done work in this example. Take a frictionless surface like this. We need to imagine this now, because in reality, no surface is a frictionless surface. So on this frictionless surface, imagine that there's a ball, and this ball is rolling without force because the surface is frictionless. So this is the displacement. Now, taking the formula of work done as F times D, we substitute the value of force as 0. And we get work done as 0. So, in this case, there is no work done. So you have seen in the previous two examples that if either force is 0 or displacement is 0, then the whole work done becomes 0, alright? Now that's because the formula of work done is like this. Work done W is equal to force times displacement. And if either force is 0, work done becomes 0, or if the displacement is 0, work done also becomes 0. Now what we are going to see is, we're going to see what happens to work done if the force makes some angle theta with the displacement. Tichan, ready for the next demo?
Yes.
Yeah, please come. Alright, now in this example, what do you notice is that the direction of force is upward. See, she's applying force in this direction. And the displacement of the body is in this direction. In which case, you notice that the force F makes an angle theta with the displacement. So in this kind of example, do you think we can use the formula of work done as simply F times D? No, we cannot use this formula. This time, if the force makes an angle theta with the displacement, then our formula for work done becomes F times D times cos theta. For the next demonstration here, I have my son ready. So Duxel, you will lift the trolley and move straight forward. Alright, that's it. Okay, no, you just keep the trolley lifted up. Okay, so in this example, what you notice is the direction of force is upward because he's applying an upward force to lift the trolley. And with the position of the trolley like this, he is moving in the front on a horizontal surface, which means that the displacement is in this direction. So in this example, what did you see? The force and the displacement is perpendicular to each other. So here we use the same formula as force times displacement times cos theta. And the value of theta here is, since the force and displacement are perpendicular, it's 90 degree. So just substitute cos 90 in this formula and you will get the work done. Now very interesting. See, you lift the object and you move straight, front or back, okay? But the surface has to be horizontal, in which the force and the displacement is perpendicular to each other. Now, you might be very tired because you're lifting the object and you're moving in the front, okay? But here again, since theta is 90, and if you find out the value of cos theta in your calculator, then it's equal to 0, which means the total work done is equal to 0. Okay, so the first concept you have learned right now is work done. And you have seen that the formula of work done is force times displacement. Alright, and what is the definition of work done? If you know this formula, you can make up your own definition. So if I make my own definition, then I would say work done is the product of force and displacement. So after getting the definition, getting down to the formula, now the last thing that you need to know under work done is the unit. So what is the unit that we use to measure work done? Okay, now as you can see here, force is measured in Newton, displacement is measured in meter. So you have Newton meter, and this Newton meter is called as joules. All right, Joules, joules. But if you abbreviate it, it is capital J. So the SI unit of work done is joule. The next kind of work done is called work done against the gravity. So if I may show you an example, here is the load that I'm going to pick up from the floor. So if you have the object on the floor like this, please remember that now this object has two forces acting on it. One is the force due to gravity, which is downward like this. Gravity has the tendency to attract any object towards it, so that is one force. The next force is the force that I'm applying upward to pick up this book. Okay, so when I pick up the book from the ground like this, then this is the displacement. But right now, the displacement has to be replaced by h. H means height above the ground. Okay, so here now, what happens to the formula of work done is, we're going to use the usual formula of work done. Work done is force times displacement. But the force here has to be replaced with m times g. M refers to mass of the object, g refers to acceleration due to gravity. Because this book, when you raise up to a height from the ground, it is being pulled by the gravity. And the displacement of the object, we have to replace it as h. H means height above the ground. So what happens to our formula is now, work done is equal to mgh. So mgh means the product of mass of the body, g means acceleration due to gravity, and h means height above the ground. So now we're going to learn the next concept, which is power. And like I said before, the concept of power incorporates both work as well as time. So for that, I'm again going to make my children perform this simple experiment. So I have 10 balls in this first basket. So I'll have my stopwatch here, and then my kids are going to transfer this ball one by one as fast as they can, and I'll record the time. The formula to calculate power is work done divided by time. So if work done is measured in joules and time taken is measured in second, then the unit for power is joule per second, or to be precise, the unit for power is watt. Capital W stands for watt. In this demonstration, you have seen that the work done is same, and we are assuming that the work done is equal to 200 joules because both the kids were transferring equal number of balls from one basket to another basket, which is 10 numbers. But we notice that there is difference in time. So let's calculate first work done power of Truxell. So the formula of power is work done by time, and if we substitute the value, the work done is 200 joules. The time taken was 10 seconds. This gives us, on simplifying this, you get power as 20 joule per second, because you have joule per second. And like I said before, joule per second is watt. So power of Truxell is 20 watt. If we look at the power of the Chen using the same formula, we have the same work done, but time is different. So if we calculate it, we get the power of Tichen as 18.18 watt. So here, what did you notice is power is the rate of doing work. It depends on how much time is taken to complete a work. Now let us learn the third and the last concept for today, and that is energy. Well, the entire universe is composed of two things, matter and energy. And as you have learned in the lower classes, there are many forms of energy. Chemical energy, light energy, sound energy, electrical energy, heat energy, mechanical energy, and so on. The list will go on like that, okay? But in today's lesson, we are particularly going to learn about mechanical energy. So what is mechanical energy? Mechanical energy is the energy possessed by a body due to its position or motion. Please note these words, due to position and due to motion. So if we break down the definition, then we get two types of mechanical energy. One due to position and one due to motion. So the mechanical energy due to position is called as potential energy given by mgh. M here stands for mass of the body, g for acceleration due to gravity, and h for height above the ground. Then the mechanical energy due to the motion is called as kinetic energy, and kinetic energy is given as half times m times v square, where m stands for the mass of the object and v stands for the velocity of the moving object. Alright, now to demonstrate the two types of mechanical energy, I have my son here ready with his crossbow, and as you notice here, this is the arrow which is already loaded. So the arrow has potential energy because right now the arrow has a position or a state. So now if he shoots the arrow, yes. So what you notice here is the arrow, when it was shot from the crossbow, it possessed motion. And that energy due to motion is called as kinetic energy. And as you have seen, the kinetic energy of that arrow was able to knock the PET bottle off its place, because any object that is moving has the ability to transfer its energy to another object. To explain more on the kinetic energy and potential energy, I'm going to use this PhET simulation. And if you notice here, this is the energy graph. The green shows kinetic energy. This shows this is the potential energy. For now, please ignore the thermal energy. We don't need this. And this one here shows the total energy. And this speedometer here will tell you the speed of this skateboard player. Now, if I may start at this extreme position, if you notice the energy graph, it shows potential energy but no kinetic energy. That's because this body is at the highest point from the ground, okay, and this body is in a state of position. So the energy associated with position is called as potential energy. Now, if I allow this body to descend, then see what's happening here is, do you notice that the kinetic energy is increasing, whereas the potential energy is dropping down? Potential energy is dropping because the player is coming closer to the ground. So h, the value of h is decreasing. And at this position, the skateboard is at the ground. So h here is 0. And this is shown here in the graph. Potential energy is 0. But the body possesses the maximum kinetic energy. Alright, so here as the body ascends uphill, do you notice that the potential energy from 0 is increasing? That's because, as I've said, the height from the ground is increasing. So potential energy increases, whereas kinetic energy decreases. And at this extreme end on the other side, the energy is totally potential. Kinetic energy is 0. So I will play this PhET simulation for a while, and in the meantime I want you all to look at this graph here. Do you see that the kinetic energy increases, decreases, potential energy increases and decreases? So here you notice that kinetic energy is changing to potential energy is changing back to kinetic energy. However, if you look at the total energy, it doesn't change. It remains constant throughout. That's because there's a law, and this law is called as law of conservation of energy. So how does law of conservation of energy state? It states that energy can neither be created nor can it be destroyed, but one form of energy can change to another form. And in this process, the total energy remains same, or total energy remains constant. So today we have learned 3 very important concepts in physics, and if I may repeat, it's work done, power and energy. And before I wrap up the lesson today, I want to leave you all with a question. Please try this question. It's not so difficult also. So the question is, a truck of mass 8,000 kilogram and a car of mass 1,000 kilogram are moving at the same speed. So which body has greater kinetic energy and why? So with that, it brings us to the end of the lesson today. I hope you all enjoyed as much as we did today. So thank you very much and take care, everyone.